very much. It's great to be at this very stimulating workshop. I'm going to give a talk that's a bit different from most of the ones that we've heard, in that I'll give a couple of physics vignettes, but the arc of the talk is looking toward how can we build tools to have more systematic stacks so that we can have one sample that is very much like another sample, and so I'll talk about that. All right. So I think that most of you, in different ways, are familiar with the approaches to making stacks of graphene and other van der Waals layers, and those have built on lots of developments, many of them at Columbia, and then a key development about 6 years ago, or a bit more than 6 years ago, by Pablo Herrero's group and Emmanuel Tutek's group, on being able to control the twist angle of two layers. And so what this allows us to do, these are just cartoon pictures. Here's a honeycomb lattice representing one graphene layer, and now another layer, and we can see a moiré. And in principle, we want to be able to control the twist angle and make the structure that we intend. And so let's explore how this actually plays out. I think that I'm going to basically flash through this, that I think you all appreciate why it can be exciting to make twisted van der Waals stacks, because of the degree of control and the degree to which relatively simple theoretical calculations can give surprisingly quantitative answers, meaning that we can hope to do design of structures and then see what electron-electron interactions do, because the calculations are not as simple. Let me just tell you where I'm going to be going with the talk. As we've seen, the electronic structure depends on lots of details of the stack structure, and I'll go through what some of those are. It can be really powerful to be able to do Bistritz or McDonald style calculations. I'm still stunned that their calculation more than a decade ago was able to say what the magic, not only that there should be a magic angle in twisted bilayer graphene, but pretty quantitatively what it would be, and it continues to be very informative. We need to be able to control the spatial structure, because the spatial structure has such a tie to the electronic structure. And what we've come to is realizing that as we try to develop better ways to control the spatial structure of a stack, we need a way to efficiently and accurately evaluate that structure, because if not, we're sort of flying blind. So let me give you the two promised physics vignettes. The first one I'm just going to wave my hand at, because there was a lot more discussion on the first day of the meeting of Chern insulators, orbital magnets in van der Waals systems. But let me just remind you that when, as a culmination of a lot of work by a number of groups, notably Eva André's group on twisted structures in van der Waals materials, in 2018, Pablo Herrero's group really supercharged this area by showing superconductivity in twisted bilayer graphene. And so many people set out to try to reproduce and extend this. And Matt Jankowitz was the first, working at Columbia at the time, was the first in another group to do that. And since then, there have been hundreds of samples around the world that have shown superconductivity in the system. But my group's first attempt to reproduce this, which was work by my then student Aaron Sharp, did not show superconductivity. Instead, it showed a very large Hall effect, and one that was hysteretic with magnetic field that with discussion with the community, we quickly realized was representing an orbital magnet, and we suspected that this was a Chern insulator, but with some disorder that meant that we were not getting quantization in the system. Why did our sample not show superconductivity, instead show this very different behavior? A clue was provided by photos that Aaron had taken while he was making the sample. And here I'll just, to help show this, you can see this large structure is one of the boron nitride layers that the graphene was, the two layers of graphene were encapsulated between. And here's one of the layers of graphene, and you can see that the edge of the graphene is aligned with the edge of the HBN. And based on this optical image, we could see it was within about 1 degree. This was unintentional. People had generally considered HBN to be an inert cladding layer that was just very good at protecting graphene from the outside world. But the community had known, and Pablo's group and my group had both done studies on graphene on HBN going back 5 years, and seen that there can be a strong effect on the electronic structure of monolayer graphene from boron nitride, particularly when they're aligned. And so it shouldn't be too much of a surprise that this could have an impact. And so we gave talks about the electron physics results, and we said, it seems to be important that the graphene and boron nitride are approximately aligned. And Andrea Young's group looked at their catalog of samples and were able to find a sample that also seemed to have graphene boron nitride alignment. And they not only reproduced our results, but did it more beautifully. They were able to see that, as we had only suspected, that the Hall effect was in fact quantized. And so this showed it really was a Chern insulator. And there's a lot more to this story, but as I think you've seen earlier in this conference, though this was, to my knowledge, the first known orbital magnet at zero magnetic field, now those have proliferated. Here's just one example from work that I did in collaboration with Feng Wang and Yanbo Zhang on rhombohedral graphene ABC trilayer aligned with boron nitride with a displacement field. But there's a proliferating list of these, including most recently work by both Longzhu's group and Xiaodong Shu's group, and the Cornell group of Jia and Fai on different versions of fractional Chern insulators in Moiré systems. So this has been a proliferating area, very exciting. But what about twisted bilayer graphene? So I showed you that we had seen this behavior in one sample, and then that was studied by Andrea's group. So there have been hints, and I think this is developing into more than hints. So Dima Efitov's group has seen a sample where at a different filling, and maybe now also including at the same filling, has seen orbital magnetism at zero magnetic field. But most of the cases, they're stabilized by magnetic field. Work by Amir Yacobi's group seems to show Chern insulators that go almost down to zero field. And then there are STM works that show the local structure of the sort of swirly wave functions associated with these orbital magnets. But these two original samples, both Andrea's group and my group, have done a lot more studies on our respective samples, including with different techniques, and have learned a lot from them. But they remain the only two of their really of their type in the world, though I'm hoping that that's starting to change. So what's going on? Why is it that more than 5 years later we still haven't gotten back to that behavior in those samples? So here again is the honeycomb lattice of graphene, another layer of graphene. Now I'm going to show you boron nitride laid on top of this, and the twist angles shown here are the ones that we extract from our electrical measurements that we can determine the areas of the Moiré cells, and these are also consistent with what we can see in our optical microscope image. So here's how the boron nitride lattice lies on top of the twisted bilayer graphene. And to me, the really striking thing is that the moires are almost perfectly matched. So they're not only almost the same period, but they're actually almost the same orientation. And if you think about this for a moment, you can see that that's quite non-trivial, because the graphene moire is coming from, well, let's say graphene boron nitride. If you had 0 twist angle, then the moire would go along the original lattice directions. It would just be an expanded version of the lattice. But a moire from a twist is along the theta direction. It's 90 degrees off, or 30 degrees off if you prefer. And so if you had graphene aligned at 0 degrees to boron nitride, you would never have the two moires lying on top of each other. So there has to be a small but non-zero twist between the graphene and the boron nitride. And actually, these images are ones that that I made at the time because I was wondering, what's important? Do we just need to have a small graphene boron nitride twist to break the C2 symmetry in the system, or does it need to actually have the moires match? And my suspicion at the time was either you just need a small, some twist that's close to 0 so that you break the symmetry, or if you need to have a precise twist, then maybe nature is kind and it likes to lock in to that structure. And that's actually something we've seen since then. Many of you know that in alternating twist trilayer graphene, that the first and third layer like to lie on top of each other. If you didn't perfectly match the angles of the first and third layer, they'll get closer in the region that they're overlapping. So what do we really need? So I'm doing this based on work from Alan McDonald's group from 2021, but there was contemporary work by Senthil and also by Paco Guinea, and there may be others that I'm missing, that all came to basically the same conclusion, that there's a reason that that matching the moires matter. So what I'm showing you here is a very specific angle for graphene and a very specific angle for graphene and boron nitride that lead to the two moires sitting on top of each other. So there's one choice of angle. There are two, in fact, because you can reverse the graphene boron nitride twist. But this shows why unless things like to relax to this, you're not going to get it accidentally, because not only do you need to get about 1.1 degrees for the graphene angle, which we know how to do, although my understanding of the state of the art in the field is that no one really can hit this to better than 1/10 of a degree, and actually a substantial fraction of the time it will be off by a degree or more, and you either throw that sample out or find something interesting and you say, oh, that's what we intended in the first place. So this is doable, getting close to 1.1 degrees. It's more challenging to get the graphene boron nitride angle because you can't use the tear and stack or cut and stack trick, starting with one crystal and rotating half of it with respect to the other. Here, these are two different materials. So I'll come back to how one can approach that. But first of all, you should hit both of these angles. And I would say somewhat impressionistically, Alan put on this blue blob saying, how close do you need to be? And that's supposed to indicate how close do you need to be so that in transport, a region of a single churn number will percolate across the sample, and therefore in measurements you'll see something that looks like a churn insulator. So I've also added onto this a representation of of where in this angle space the sample from my group sits and where the one from Andrea's group sits. And I put 2 copies for Andrea's because I don't actually know which way the graphene is misaligned with respect to the boron nitride. But what you can see is that both of them are pretty close to this, this ideal commensurate condition, and Andrea's was even closer. And so, this all sort of hangs together. It makes sense. So, so what we're seeing is that now there's not just one tuning knob, but a second tuning knob, a second twist angle, and this is representative of the problem in this space, which is also, of course, an opportunity that that you can tune so many things, or so many things can differ, and so every sample is different. And we'll see in my second vignette that strain, even quite small amounts of strain, can make a strong effect. And unfortunately, we don't yet have the ability to control these very precisely, although the ability to control them reasonably well is what really kick-started this area. So let's get to this second vignette, which comes from one of our attempts to reproduce this, this orbital magnetism. So here you have on a semi-log scale, so a log scale, there's resistivity, longitudinal resistivity, and on the horizontal axis, we have the filling of the sample going from charge neutrality up through fully filling the band on the electron side, fully emptying the whole band. So this represents adding 8 electrons per moire in total. As you can see, we didn't hit the magic angle that well. It's nearly 1.4 degrees on this part of the sample. And if you look at this, it's pretty featureless. It has a peak in resistivity at the charge neutrality point. It has strong, very resistive peaks at full filling and full emptying of the bands, so where we're in non-interacting band gaps, but we don't have the correlated electron insulators that are familiar from near the magic angle, and so it looks pretty pretty generic, pretty standard for this sort of angle. And I do want to point out, since Shankar had asked during his talk, what's the mobility in these sorts of systems, and our estimate of that based on just as we put half an electron per Moiré, we're at about 100 ohms. And so that corresponds to about 120,000 centimeters squared per volt second. So I don't, to convert that to a mean free path, we have to say what's the effective mass, and or what's the Dirac velocity. So I'd be happy to discuss that with people. I'm not even certain whether this is limited by the sample size, but this gives you a sense of, twists don't necessarily make a really dirty system at least away from the magic angle. It seems like one can get reasonably high mobilities. And near the magic angle, our resistivity is at least several times higher, and it's harder to pick out, it's harder to say for certain a mobility. So, so this looks pretty generic, but then let's turn on a magnetic field. So, so here we have a selection of magnetic fields going up to 2 Tesla, so relatively modest. And what you see, again, this is a semi-log scale. The resistivity over broad swaths of density on both the electron side and the hole side just shoots up. And in the greatest case, it rises by a factor of 300. So that's a really large magnetoresistance. It's not, absolute world record, but it's particularly unusual because it's over a broad range of density. And normally, the simplest mechanism that people tend to invoke for strong magnetoresistance of this kind is having nearly compensated electron and hole pockets, which it's not clear how you would maintain those over this broad density range. So that was really pretty surprising. You also see all of these wiggles here that are quantum oscillations. we'll look at that in a moment. So there are these strong regions of magnetoresistance. Now let's do a cut in magnetic field within one of these magnetoresistance regions. And so what you see is that, again, there's strong magnetoresistance, and then we start to get oscillations. And the magnetoresistance is quite close to quadratic. The oscillations are a little unusual. Where we would expect a Landau level, we see a doubling on two dips that are split off from the expected location. And if we put all of this together and now look at a color map of a Landau fan, here's how it looks. So this is, again, density on the horizontal axis, magnetic field on the vertical axis, and we can label Landau levels, and these are the magnetoresistance regions on the two sides. And what you see is that splitting that I mentioned, half of the Landau levels terminate when they hit the magnetoresistance region in the fan, and half of them split into two and when they reach this region, and then they cross the split Landau levels coming from fully empty or fully full, and there's a quite ornate structure where they cross. So for about a year, Joe and I talked with anyone who we could grab by the collar and showed them these data, and uniformly the statement was, you know, it's beautiful, I've never seen anything like it, I have no idea what's going on. And after a year of that, Joe got pretty frustrated, and he said, I'm going to take matters into my own hands. And even though I said that the calculations are relatively simple, we all know that for someone who hasn't specialized in it, you know, doing a Bistritz or McDonald style calculation is not all that simple. So Joe decided to start with just Hofstadter butterfly, because, you know, looking under the lamppost for your keys, doing what he could do, even though he knew it wasn't the right model for this. So Joe just did standard calculation of a Hofstadter spectrum, the spectrum of a system with a spatially periodic system with finite flux threaded through it, and the model that he basically started with the standard Hofstadter butterfly and then added tweaks to it. He added anisotropy, so hopping different in the two directions. Again, this was a square lattice, so just different in those two directions. And then he added something that only later did I learn was a bug. He had been writing his code, and he accidentally induced hopping, next nearest neighbor hopping. So there was anisotropy and next nearest neighbor hopping, but when we posted this work on the archive, two great things came out of it. One was that Dan Parker contacted us and said that you know, he saw that we could achieve the same thing just with an energetic splitting between two species of electrons, and so we now understand that to be basically a Zeeman splitting. And so he and Ashvin collaborated with us and became co-authors. And the other great thing to come out of it was that Matt Yankowitz said, I actually have samples from way back that did show similar behavior. And so now it was not just one sample in the world, there were 3 samples. And since then, Joe has made some more once he understood what the ingredients were. So this is now still not a proper Bistritz or McDonald calculation. This is just a calculation of compressibility for a system now on a triangular lattice, just to be a bit closer, and you see a factor of 2 anisotropy between hopping in 2 directions, and a Zeeman type splitting between the two sets of electrons. And if you look at this calculation and the data, they really bear a pretty remarkable resemblance, especially when you consider that this is nowhere near a microscopic model for the system. There's a lot of detail that's matched, including how these crossings look. So Joe had a pretty clear sense that, that we were on the right track, but still what that meant is, all right, we have this anisotropy. Where does that come from? We suspected that it probably came from strain. And so we were fortunate to connect with Oscar Vafik and his then postdoc Xiaoyu Wang, and they had the tools to do a more serious calculation with a really more appropriate model. So this is just a selection of the data again, showing the strong magnetoresistance region, I just want to point out one thing that I didn't show you before, which is that if we measure the Hall numbers, so we take the Hall effect and we just take the inverse of that and infer what the density is, you can see that that out to more than 1 electron per Moiré, nothing's really happening. You're just adding electrons in a very simple way to a band. And then something happens in the middle here in this magnetoresistance region, and then there's a jump, and again you have the same slope of the Hall density. This is familiar from the cuprates, where you go from electron-like to hole-like pockets. And so it was clear to us that what was happening here is that we were crossing a Van Hove singularity and going from electron-like to hole-like. It turns out we were wrong. And Xiaoyu pointed that out to us. As some of you may know, there are 3 degenerate Van Hove points without strain in these systems. But if you apply uniaxial heterostrain, that is stretch one layer with respect to the other in one direction, then the 3 points are split out to different energies, and what that ends up meaning is that that as you fill carriers into here, 2 of the Van Hove points are representing boundaries between having a closed Fermi surface and then a 1D-like open Fermi surface. That's the first of them. And then the second of those is when you again reclose into a new closed Fermi surface. So that's 2 of the Van Hove singularities, and those bound the region where we have strong magnetoresistance. But then there should be a third one, and the third one is shown here. Well, in Xiaoyu's calculations, which I'll show you in a moment, you'll see that there's a kink that occurs right there. And in fact, we had seen that in the data and noticed it. So here's in the calculations, these are just Boltzmann transport equation calculations, whereas before we had just done thermodynamic calculations, the spectrum. So you see there should be a feature here at the third Van Hove singularity. And Xiaoyu pointed out, well, when you cross that, you're going from 2 Fermi surfaces merging into 1. And so you should see that in quantum oscillations. So fortunately, Joe had taken the data on this during COVID, and he just let it run forever and take a very dense set of data, so he was able to mine that to get the data out. And what you see is, as a function of density, let's say at a high magnetic field, you see complicated oscillations, and then at some point in density, they become very simple. And so if we take a Fourier transform of this, what you see is that that at low densities, you have 2 frequencies, and then that terminates, and you just have 1 frequency. Now, the 2 frequencies, there's also the sum of the 2. That's an artifact. It's just the nonlinearity of the analysis. But you can see that that this matches quite well to the calculation, where we're just invoking a strain of about 0.2%. So the message here is that away from the magic angle, you can get really good description of the electronic behavior from Bistritz or McDonald style calculations, and in this case, we had unintentionally put strain on, and it turned out that part of the sample had extremely spatially uniform strain. But 0.2% strain is not a lot, and it shows up routinely in SDM measurements. So you can get big effects from small tweaks, and you can understand them very well from calculations. But here, we didn't directly put on that strain intentionally. So the problem is that there's lack of structural control, both in terms of values and in terms of uniformity. I'm showing here beautiful work from Ave's group, where they showed they could use ambient room temperature AFM to map out a Moiré, and you can see it's not uniform spatially. So, general approaches to this sort of problem, you can do what 95% of the field has done, which is to make many samples and focus on what you find that's interesting, and that's been very fruitful. You can make the inhomogeneity into a virtue, use a scanning probe and look locally, and you find everything in one sample. You can intentionally create a gradient. This is showing a cartoon from work by Corey Dean's group, straining a ribbon. You can have an in situ tuning. This is showing work from Shachal Ilani's group on what he calls the quantum twist microscope. And in each of these cases, I'm just giving representative examples. They're not alone in doing that. And finally, you could try to improve stacking. And I'm taking that approach because I think all of these have a lot of value. But as we go to stacks that have more layers and more parameters, I don't think there's going to be one knob to turn that will do everything for us. So this is just a picture of the vacuum stacking system that Andy Mannix's group and mine built based on his pioneering work in that area. But we realized that we didn't have a way to determine, how were we doing on our stacking. And so inspired by that work from Columbia that I showed, we wanted to map out what we were seeing in a way that was not just indirect, not fabbing a sample, cooling it down, making electrical measurements, and indirectly inferring the parameters, but trying to directly measure the structure. So we set out to use AFM to do this. This is an image of a sample on its stamp before we've encapsulated it with its bottom layer. Here you can see we've mapped using an AFM-based technique the moiré of monolayer graphene on boron nitride, and we can actually even see the atomic lattice of boron nitride. Here's an example of a moderate scale image mapping out the moiré. We can go to larger scales, so this is about 0.5 micron in total. You can see it's a quite uniform moiré. We can zoom in further, and you can see the atomic lattice scale information as well as the moiré. And I've shown you pretty uniform structures, but if you look over larger areas, you can often find bubbles and inhomogeneities. And so this allows us to really determine what structure have we made, and to do it, to make the structure and then take it out of our stacking system in an hour on a commercial AFM platform using this torsional force microscopy technique, image it. So that work is published, and happy to answer any questions. We really want to make this accessible to everyone. And finally, I know I'm over, but I just want to say those are pretty pictures, and they do tell us a lot, but really what we want to know is quantitatively, what is the structure that we've made? And what I showed you so far wasn't really enough for that. We could take the Fourier transform of an image, and that gives us periods in different directions, and we can try to extract twist angle and strain, but there are distortions. And so if you just take that image and you tried to extract the wavelength in the different directions, you'd get these values on top. But if you correct for the fact that the scan was not in fact the size that we thought it was, and it's not square, then if you use the sensors on the piezos, then you get a very different answer that would represent not 0.9 degrees, but 1.1 degree. And when we take into account those distortions, this is sort of what I would like is that the takeaway, we can really get the wavelengths in the different directions very tight, and then we can extract a twist angle that in this case was 1.125 to 1.127 degrees, and a strain that's extremely small, much smaller than a hundredth of a percent. So on this particular sample, and we've built an analysis pipeline that can be used on any AFM images, we can really surprisingly quantitatively extract structure. So again, the electronic structure depends on tremendous detail of the stack structure. 1/100th of a degree matters. A 1/10th of a percent twist strain matters, and we need to be able to control spatial structure to compare with what can be done in calculations of electronic structure. And so now we have a way to see what we've made, and so we're starting to use that to try to tune and improve our stacking. And this work, the key people who drove this in my group were Aaron Sharp and Joe Finney, who were then students in my group, Mihir Pandarkar, who's a postdoc in my group, Stephen Tran, who's a student in my group. Mihir and Stephen did the AFM-based mapping. And I'll just leave it there, and happy to take questions.
Great, we have time for some questions. Okay.
So when you quantified the disorder, you mentioned some pretty high mobility number, but I wonder if the mobility is the right way to quantify disorder in this context. I'm asking because, for example, in gallium arsenide, we know that a sample with higher mobility may actually have much poorer energy gap. And so what about this situation? Maybe you have a longer range disorder where mobility is not the right way to quantify.
Yeah, so I think that's an excellent point. The point was, I mentioned a mobility number. How representative is that of what the disorder is? There may be recent work on transport in a disordered Moiré, so where there's twist angle variation. I haven't seen that yet, and it's actually, I think it's very different kinds of disorder compared to what we're used to in ordinary 2D electron systems. So I certainly think we shouldn't hold up one number and describe it. I think we should be talking about what's the structural disorder, what is the impact of that, and I don't know how well that is known so far.
Thank you.
More questions?
You have more data points on that figure.
Yes.
Can you explain what they are?
So this image here?
Yeah.
Yes. So this is including more of the information that was in the original McDonald paper on this commensurate match Moiré, and I just showed these big sweet spots. But there are other commensurate structures that are higher order commensurability, including one that's not so intuitive, right at 0 degrees. But you can see that the blobs are smaller, meaning that there's a smaller target to hit. Okay. So since we're having trouble hitting this blob, we're focusing on that to start with.
Thank you.
Thanks for the nice talk. Near the beginning, you pointed out something like up to a factor of 300 increase in the magnetoresistance. Yes. Around equals -2, -3. Do you think you arrived at an explanation for that? Did the triangular lattice Hofstadter model sort of?
So yes, sorry, I stepped through that too quickly. So the question was, why this magnetoresistance? I created the mystery. I didn't properly resolve it. So, so I mentioned that that there are these there are 3 Van Hoff singularities, and 2 of them bound a region where the Fermi surface is extended in one direction. And so it turns out that, as we've already heard today, many things were calculated in the Soviet literature in the past. It was known that 1D-like Fermi surfaces, the extended Fermi surfaces, can give rise to quadratic magnetoresistance, and indeed, in a more specific way for this system, Oscar and Xiaoyu did a Boltzmann transport calculation and found this behavior.
Thank you. I have two questions. So first, can you comment a little bit on the working principle of torsion force microscopy? For example, how does it compare with the lateral force microscopy? What's the advantage?
Great. So for that question, the question was the AFM-based images that I showed. I didn't explain how that works. That's not that I'm keeping any secrets. It's published, and I'm happy to talk with people here. But it's called torsional force microscopy because we're instead of driving the diving board cantilever that the AFM tip is on in the normal way, instead we're causing it to move torsionally, which means the tip sweeps across the surface. This is on a resonance which is around 1 megahertz for typical AFM cantilevers. And so if we compare to lateral force microscopy, where we're sweeping across the sample and looking at how the tip is sort of dragged, here we're moving it back and forth very rapidly, but both of them should be related to friction in some way. I think of it as taking an oscillator and coupling it to the surface, a mechanical oscillator and coupling it to the surface. And my cartoon picture is, imagine that you have a sharp pencil and you're sweeping it over a smooth surface. It's going to slip nicely. But if you turn it over and you're pressing the eraser into the surface, then you're trying to move the pencil and it's harder to move it. And so I think that may be what's happening when we're in regions that are buckled in the moire and we're pressing into it, that the tip is sort of pulling the top layer of the moire with it. But we really don't have a good microscopic picture, and there's even some mysteries about, why do we see structure that looks more honeycomb-like instead of triangles? Yeah.
So is it in contact or?
It is in contact. So we are feeding back, we're pressing in with a force, and it turns out that what's important is the pressure that we're pushing with. So depending on how sharp the tip is, if it's a sharper tip, we don't need as much force. So we're pushing and feeding back on that force, and then we're oscillating in this direction and tracking the motion, the corresponding motion.
Thank you, David. I have a second question. So have you ever measured the corrugation, like how much corrugation there is in this Moiré structure? I'm just curious.
The correlation means?
Corrugation, like.
Corrugation.
Yeah.
So if we do topography, it's very, very subtle. So it's almost invisible in topography. We see it only when we're using this mode of imaging.
I see. Thank you.
But I'm sure there is corrugation, but maybe can Ellie do one more?
Yeah, let's take one last question.
Regarding regarding the sample, the strain that you have there, two questions or maybe three. What's the pseudomagnetic field that you get from the calculation? The second question is, what's the size of the sample? And third, how do you engineer a uniform pseudomagnetic field of a reasonable size?
Okay, so let me start with the easy part, the size of the sample. The sample is about 20 microns in one direction, and the Hall bar is around a micron wide. I don't remember exactly. So we have 9 contacts on each side, so 18 contacts plus the current contacts, and we set up electronics to measure them all simultaneously, so we can see how much does the twist angle vary across it. So that's the size of the sample. We're measuring between 2 contacts. It's around a 1 micron region, but maybe it's 2 microns between contacts, but we have contacts spaced all along it. What is the, how uniform is the twist? It ranges over most of the sample from 1.3 to 1.4 degrees, and it seems like some of the places in the middle, it's extremely uniform between contacts, but it's not over the entire space, and also nearer to the ends, it definitely diverges more. In terms of the pseudomagnetic field, I guess I'm used to thinking of curvature giving rise to something that is analogous to a magnetic field. Here, I think there's very little curvature. It's stretching, and so maybe we can talk offline about what that maps to in terms of a.
But the uniaxial strain will not give you a pseudomagnetic field. So.
Yes, that's correct. So I don't think that. Yeah, I think that there's very little pseudomagnetic field here.
Okay.
But we can discuss. Thanks.
Let's thank David for the wonderful talk.
Thanks.
And our